Alright guys, welcome back. We're now going to talk about boosting, and boosting is basically, in a way, we can see it as the complementary of bagging. While bagging had the goal of decreasing variance of base learners, base estimators, boosting has the opposite goal. It has the goal of decreasing the bias of high bias base learners, base estimators. Boosting shares some similarities with bagging, but it has some profound difference. So some of the similarities is that it combines results, from several base learners, and it uses decision trees, usually as base learners, as base estimators, as default at least. And so also in this lecture we're going to use trees. We're going to see boosting basically with trees. However, there are also some differences between bagging and boosting. In boosting, the base learners are also known as weak learners because they have a high bias, so they are weak learners. They tend to make poor predictions on the training dataset. And also, while bagging can be seen as a sort of parallel algorithm where we have independent bootstrap replications each time, in boosting, boosting can be seen more like a sequential algorithm where we sequentially estimate the different algorithms. And the results of the estimates at some iteration depends on the results obtained on the previous iteration. Okay, so there is this sequentiality in the working of boosting. So the definition of weak learner in boosting is technically learners that can do just slightly better than random guessing. Okay, so if I am, for example, in a classification case and I have two classes, like boosting doesn't need to use strong learners, good learners, but it needs only learners that can do just slightly better than, for instance, the toss of a coin, okay, that I will use to perform a prediction. Okay. Another difference between boosting and bagging is that, of course, since we are working with weak learners, so high bias and low variance learners, the trees, for example, used as weak learners in boosting are shallow, unlike bagging in which we used, very deep trees. Here we prefer to use very shallow trees, so that they have a maximum depth ranging between 1 and 8 more or less usually. So this is the goal in boosting. This is the setting in boosting. The boosting estimator, typical boosting estimator, so the prediction of boosting can be represented in this way as a sum over the boosting iterations, and the final number of iterations is denoted with capital T here, which is the analogous of capital B in bagging. So the sum over these iterations of a quantity, a fixed quantity called learning rate or step size, or also shrinkage parameter, times the prediction provided by each weak learner at each iteration. Okay, so it's basically a weighted sum of such predictions. All right. Now, before we start seeing some specific types of boosting, I want to show you a bit the general working of boosting, how it works in general, and then we're going to see some more specific boosting methods. All right, so the general algorithm for boosting can be summarized as follows. We start at some iteration. We start at iteration 0 with some arbitrary prediction. For example, what is done in practice is to predict a constant values for all the units in my training set, Okay, we can call this starting value f0, okay, which is the value of my ensemble of my boosting prediction at iteration 0, and it can be set equal to 0, for example, for all units, or equal to the sample mean in case of regression. And so this value is gonna be constant. You have to imagine a constant value for all units, and of course this is a terrible prediction as a starting value, but it's useful for our purpose in boosting. And now comes the trick. So after iteration 0, we start the proper boosting iterations, and every time we perform the following 3 steps. First, we consider the residuals between the target, the observed target that we want to predict, and the residuals, okay, of our boosting estimator, okay. So if we start at iteration 0 with a constant value, imagine we start at 0, and imagine that, for example, for a unit, the prediction we want to, the target we want to predict is here, okay. So the residual at the first iteration is basically equal, if we start by predicting 0, is equal to the target value, okay. And so the first goal is to consider this discrepancy between the prediction of the previous iteration and my target, and then if we use this discrepancy as target for this iteration, and we train the weak learner on this new target, on these residuals, okay. And once we have done this, we obtain the prediction of the weak learners, denoted by like lowercase f t at iteration t. And then we simply update the results of my ensembles, the prediction of my boosting algorithm, by considering the predictions at the previous step and adding the shrinkage parameter or step size times the new prediction obtained for the new residuals. And you can imagine that this, of course, will give us a new prediction that is a bit closer to the target, okay, but not quite. That will also depend on the step size. But the thing is, at this point, I'm a bit closer to my target, okay? And I have a new residuals that is allegedly smaller than the previous one. And so I use this new residual as a new target at the next iteration. I train a new weak learner on using this new target, and in the end of this iteration, my ensemble will be a bit closer to my target. And this is done step by step, all right? And this is basically it. This is repeated until we get closer and closer until we reach basically the target, if the number of iterations is set large enough. And this is it. This is the main idea behind boosting. It doesn't seem too complicated, right? So maybe the implementations we're gonna see maybe are not mathematically this intuitive, but the main idea is always the same. We start from poor predictions, and we iterated several poor predictions at each step until we basically reach the ideal final prediction on the ensemble. Here I show you an example in a regression case of the main idea behind how boosting works, and I use a shallow tree with max depth equal to 2 as weak learner, and just for simplicity I use a shrinkage parameter equal to 1, but of course this is also a tuning parameter of boosting. But so here comes the idea. So on the left side you will see the prediction of the weak learners, the predictions of the weak learners on the residuals, and on the right side you will see the predictions of the ensembles on the target that we want to achieve. So at the first iteration, of course, if we start by, as I said before, if we start by setting all the predictions, initial predictions equal to 0, the residuals on my iteration number 1 are equal to my target variable, to the variable that I actually want to predict. So I will train a base learner on this first, on my target in the first iteration, and I obtain predictions that are equal to the predictions of the ensembles, because we are at iteration number 1. But now what happens? Now we're going to consider all these discrepancies between the predictions of the ensemble and the observed data points. And so these discrepancies, we're going to report them here in the next iteration in the new plot. These are the new residuals, for my weak learners. And so we're gonna we're gonna train the weak learners using these new residuals as target. And this is the new function, okay, learned by the weak learner for the residuals. Now, if we sum these new predictions to the prediction of the ensembles obtained at the previous iteration, what we obtain is the results, is the predictions of the new ensemble for iteration 2. And as you can see, now we have a nicer, at least, prediction, seemingly nicer for the new ensemble. And so this is the results of the sum of my 2 weak learners. Okay, and now what happens? We in turn we repeat considering the new residuals. Okay, you put them here. So they are the new targets at iteration 3. And what we do now is, once again, we train a base learner on such residuals. And exactly as we have done before, we sum them to the ensemble of the previous iteration. And now we end up with this even nicer, prediction, and this looks like quite a good set of predictions for my target variable. Okay, so let's now review the iterations only from the point of view of the ensemble. As you can see in the beginning, we have quite poor predictions. Okay, but then iteration after iteration, they improve step by step until we obtain a nice, function learned by our ensemble, a nice set of predictions. And of course, imagine that increasing the number of iterations will improve the final predictions more and more. So what we have seen basically is exactly this. We have we've started from very bad predictions, okay, and iteration after iteration we got our predictions closer and closer to the final target, the final point that we wanted to achieve from our target variable. And this is how it works. Now, this is the general way how boosting works. Now we're gonna see 2 particular specific ways to do boosting. One is called gradient boosting, and the reason why it's called like this is because boosting, if we use a loss function, okay, and if we try to minimize a loss function that measures the loss between our observed target and the prediction of our ensemble of our boosting algorithm, then boosting can be seen as a sort of gradient descent algorithm. Okay, and in particular, the main difference that there is between actual gradient descent and boosting is the following. We are trying to optimize, in particular to minimize our loss function, but not with respect to the parameters of the model, but with respect to the function itself. Okay, so at each iteration, instead of calculating, minimizing the loss, okay, by finding the set of parameters that minimize it, we try to minimize the loss by finding the value of the function, okay, the value of the predictions that get my my loss function closer and closer to the minimum, okay, which is exactly the same concept that we have seen right now by getting the, sorry, I never know how to center my hands. Okay, so if we get if the goal is to set the predictions of my ensemble closer and closer to the target, is the same as saying that, as we get the predictions closer to the target, we minimize more and more our loss function, okay? Because the closer are these values to my target, the lower the value of the loss is. And so this is an alternative way to see boosting, and this is what exactly gradient boosting wants to achieve. It wants to minimize the loss function exactly in the same way that we have seen in the more general boosting. Now, in order to achieve this, gradient boosting uses what are known as pseudo-residuals. And the pseudo-residuals are mathematically defined as the quantity I'm highlighting in the notebook are the negative gradient of the loss functions with respect to the predictions of my ensembles. Now, why is that? Well, the negative sign is because, similarly to what we do in gradient descent, we want to minimize our loss function, and so we try to take the negative direction. And how much we have to move is given by the steepness, okay, of our loss function at the point denoted by the point denoted by the prediction of our ensemble. Okay, so you can see this as a gradient descent. Instead of minimizing with respect to the parameters, we minimize directly with respect to the prediction. Now, all of this might seem a bit frightening to you, but let me explain this more specifically, and you will see it's actually a very easy concept. Now, the pseudo-residual in a regression case, where we use, for example, a mean square error as a loss function, the pseudo-residual of my regression case are equal to the gradient of the mean square error, highlighted here, with respect to the prediction of my ensembles, which, once we make the due calculations, is simply equal to the so the gradient is equal to the value of the prediction of the ensembles minus the observed target. And once we take the negative sign, to obtain the pseudo-residuals, we see that we basically obtain the actual residuals of a regression case. And so this is it. These are just the pseudo-residual of regression. We have seen something similar, with neural networks. When we have seen in backpropagation, we have to take the derivative of our loss with respect to the output node, and we perform very similar operations basically. And also similarly in classification, also we can make the analogy with neural networks. So in classification, let's suppose we are in a multi-class case. What we do is we one-hot encode, our target, our output variable, exactly as we have done in the multinomial logistic regression case, and also as we have done in for multi-class neural networks. Okay, so we have as many target values as the number of classes. Now, for each of these values, so for each of these classes, we train a different ensemble. So we will obtain as many ensembles as the number of classes. And then we can predict the probability of each class with the usual softmax function, which is reported in this way. And this will provide the final estimated probability of a class according to our ensemble. Now, in the case of a multi-class classification, we can use the categorical cross-entropy as a loss function. If you don't remember how it works and what it is, just review the neural network lecture or also the multinomial logistic regression lecture. Anyway, once we take this function and we take its gradient with respect to the values of our ensemble, the final value of the gradient we obtain is equal to 1 minus the probability of a class if the unit has been observed to belong to that class indeed. Otherwise, it is equal to 0 minus the probability of the class if the unit doesn't belong to that class. Okay, and this is done for all classes that we have in our data set. And once again, we take the minus sign, so we flip the probability with the 0 and 1, and we obtain the pseudo-residual also for our classification case. I left you a link to the book The Elements of Statistical Learning. If you go at page 360 of this book, you can find a table with a list of loss functions and their derivatives and their gradients with respect to the ensemble. Okay, once we know all of this, we can actually we can observe the algorithm of gradient boosting, which works. It's very similar to the one of general boosting we have seen so far, with just a couple of differences that are quite easy to catch at this point. So as before, at iteration 0, we make a constant prediction of 0, for example, for all units, and then at each new iteration, we compute the pseudo-residuals, okay, exactly in the way that we have seen right now, so in regression and classification context. Then with these pseudo-residuals, we train a weak learner, for example, a shallow tree, using the x's as inputs and the pseudo-residuals as targets, in such a way that we minimize the loss, okay? And then once this is done, once we obtain the values of the new tree, for example, we can add them to the overall global ensemble by after multiplying it also for the shrinkage parameter or learning rate, which will lead us to a new value, an updated value for our ensemble, and in turn we can start the iteration over again, recalculate the new pseudo-residual, retrain the weak learner, and so forth and so on, until we reach the predefined number of iterations. Now, before continuing, just a small observation about gradient boosting. So first of all, notice that we are solving two optimization problems. One is the global optimization problems solved by the ensemble. That's minimizing the loss function more and more at each iteration. And one is the iteration specific optimization problem, which is obtained by solving, for example, the weak learner, the shallow decision tree, with respect to the pseudo residuals. Okay, so we are basically solving a lot of small optimization problems to solve a global optimization problem, a more general optimization problem. Now, because the residuals are always continuous features, the pseudo-residuals are always, continuous values. Also in classification, you can see we have the probability -1 or 0, which are continuous values. This means that our weak learners will always try to solve a regression problem. Okay, so usually what is used here are regression trees. as weak learners. But this doesn't mean that the global optimization problem is solving a regression problem, but it's actually solving a classification one, because the function, the loss we are minimizing, is always the categorical cross entropy, for example. Okay, and so we are solving a classification problem. All right. And this was it about gradient boosting. Hope it was clear. If I was in class, I would ask if you have any question about it, but of course here it's not possible, unfortunately. So let's switch to the next topic. Of course, feel free to pause the video whenever you want, if you want to review or read better from the notebook some concepts, if this can help you. And the next topic is another very famous boosting algorithm called AdaBoost, which is actually the very first, boosting algorithm appeared in the literature, so that we can see gradient boosting as a generalization of AdaBoost. Or if you prefer, we can see AdaBoost as a specific instance of gradient boosting. Now, AdaBoost has some differences with gradient boosting, of course. First of all, it was originally conceived, and it is originally conceived only for classification, binary classification problems. Then with times it has been generalized, but the original AdaBoost is simply for classification problems, binary classification. Here then we are going to assume in this section that our targets, our labels, are equal to -1 for the negative class and +1 for the positive class, for example. This implies that also the weak learners we're gonna use for AdaBoost are gonna be binary classifiers, for example, classification trees. Okay, so also the output of the weak learners is gonna be either -1 or +1. Okay, now other differences with boosting, okay, then with all the boosting methods we have seen so far, are differences, significant differences, because are the differences that make AdaBoost a very, such an effective algorithm and represent the strength of this algorithm. For example, unlike the other boosting algorithms we have seen so far, AdaBoost assigns a weight to each unit. Okay, at each iteration, each unit is given a specific weight. These weights are determined by the fact that the unit was misclassified or not at previous iterations. Which means if the unit was misclassified at previous iterations, then they will be given larger weights at the next one, and if they were correctly classified at a previous iteration, then their weights won't be updated, basically. Okay, so that at each new iteration, AdaBoost will focus more and more on units that are misclassified. Okay. So this is what the weights are saying. The weights are saying, look, AdaBoost, at this iteration, I want you to focus more on these units, because these are the units that I'm misclassifying. And so please try to classify them correctly. Okay. All right. So this is the goal of the weights. Then the step size alpha in AdaBoost is updated as well at each iteration. Okay, so that at each iteration we have a different step size. So this means we don't actually need to tune the step size, but it is automatically computed by AdaBoost, and so that the ensembles at some iteration t can be written as the sum of my ensemble at a previous iteration plus the new learning rate, okay, times the new prediction provided by my weak learner, which I repeat, they are either -1 or +1. And so this means that AdaBoost, as we will see, is able to automatically recognize to which weak learner among all the weak learners in the ensemble, to which weak learner give more weight, which one is more important for the predictions, and to which one to give less weight. Okay, and this is because these step sizes, which I just called weights multiplied by the weak learners, and the step sizes are proportional by the amount of correct classifications made by each weak learner. And last, AdaBoost uses a new loss function that we have never encountered before in classification, which is the exponential loss, which takes this shape. And what you can see about this loss is that, I repeat, we have either targets that are -1 or +1, and so we have ensembles that are either positive or negative. When these quantities are both positive, so both the target and the ensemble, the prediction of the ensemble, or they are both negative, so the target and the prediction of the ensembles are both negative, it means that the units are correctly classified, which means that this quantity that I'm highlighting, the exponent, is positive, and the negative exponent of a positive value is a very low quantity, and so these units won't be considered very important by they won't be given too much weight by AdaBoost. However, if we have misclassifications, this becomes the exponent of a positive quantities, and so the value can grow large very easily. And so AdaBoost will try to focus much more on these misclassified, will give much more weight on these misclassified units, on this larger error, okay? And so AdaBoost will try to adjust its predictions more towards these units rather than on the already correctly classified ones. And here we see a graphical representation of this exponential loss. You see that it does something that other losses that we have encountered so far don't do. That is, give very large, importance to large when the errors become larger and larger. And this is a way for AdaBoost to say, okay, let's try to get this straight, okay? Let's try to classify them right. Here we see a representation of how AdaBoost works. We start with our normal training dataset. Usually at the first iteration, all units are given the same weights, okay? And then at each iteration, after the first iteration, we train a weak learner. We obtain the predictions of this weak learner. These predictions will produce some correctly and incorrectly classified units. And based on who is misclassified and who is not, the units at the next iteration number 2, will be weighted differently. Okay, so we will have a weighted sample based on the misclassification at the previous iteration. Now, retraining a weak learner with these new weighted units will produce new set of predictions, which means will produce new misclassification and correct classification, which means we are gonna update our weights again at the next iteration, and so on and so forth, until we reach the final number of iterations. Then the final prediction is simply given by the sum over all all the iterations of our AdaBoost algorithm. Okay, and then we simply say, okay, is this quantity negative or positive? If it's positive, we assign it to the positive class. If it's negative, to the negative class. And here we can also see an example on how AdaBoost works graphically. We have 7 iterations of AdaBoost in this case. After the first iteration, actually, before the first iteration, all units are given the same weight, okay? So the size of each point represents the weight given by AdaBoost to each point at the beginning of the iteration. So we train a weak learner, in this case a decision tree with maximum depth equal to 1, which is called a decision stamp. You see it only splits the region in the feature space in 2 parts. And this prediction produced 2 misclassifications, these 2 red points, as you can see. I'm trying to indicate them here. So this means that the next iteration we will give a larger weight to these 2 units, and this is exactly what happens here. You see at the beginning of the next iteration, if we train the same weak learner decision stamp on this new dataset, now you see AdaBoost tries to get these 2 units correctly classified, and basically this produces a new decision boundary. But now we have these blue points that are misclassified, and so the next iteration, these new blue points will be given more weight. Notice that this doesn't mean that the previous units are not given weight anymore. They're still given some weight, but now this time we're also trying to focus on the on these new blue points. Okay, and as you can see, if we train a decision tree with maximum depth 1 on this new reweighted dataset, this means we want to try to achieve correct classifications for these larger points. And as you can see now, they are all correctly classified indeed. But this produces new misclassifications for this point, which means at the next iteration, once again, we will AdaBoost will focus also on this new point, and so forth and so on, until in this case I use 7 total iterations, but of course you should use a much larger number in real applications. Also notice the value of the step size on top of each plot. Okay, this is automatically determined by AdaBoost, and as far as we can say, AdaBoost is given the largest step size to the predictions of iteration 1. Okay, so once we have obtained all these decision boundaries, all these predictions and all these weights, what we do is we average them. Actually, we sum them with each other. We multiply the step sizes with the predictions. We sum all of these across all iterations, and what we obtain in the end are the decisions of AdaBoost. Okay, and as you can see, they are very, very sensible because all points are correctly classified, and we also obtain a decision boundary that is nicely interpretable. It's very smooth, and so forth and so on. Okay, so this is how AdaBoost works. Now let's see mathematically, formally the algorithm. So in the first step, we give weight 1/n to all training units. On this weighted dataset, we train a weak learner. It can be a shallow decision tree. Then we compute the weighted misclassification error, which is the sum of the weights of the misclassified unit over the total, the sum of all weights in the dataset. We update the step size accordingly, and now you don't need to know the derivation, how the step size is derived. What you need to know, to understand, is that the step size is proportional somehow to the number of correct classifications, to the proportion of correct weighted classifications made by the weak learner. Okay, and then once we have all of this, we can also update the weights. Okay, and as you can see, this indicator functions is telling us that the weights are updated only for those units that are misclassified. Okay, otherwise this value, if the unit is correctly classified, this value goes to 0, which means that this becomes 1, and so the weight is not updated for these units. Okay, and this then in turn is repeated exactly as we have seen in these plots above until we obtain the final number of iterations, and then finally the output is the weighted sum of each individual weak learner with weights given by the step size calculated at each iteration. And this is it. This is what AdaBoost does, how it works, and this is also the last boosting algorithm I wanted to show you. Now, just a small, discussion on the hyperparameters in boosting. We have exactly like in bagging the number of iterations. In this case, though, boosting is a bit more sensitive to this number than bagging, because if the number of iterations is not large enough, then we could have quite inaccurate estimators, but if it's too large, then we might end up overfitting in this case, because at some point the variance of our ensemble will also start increasing. But however, it has been shown that in order for this to happen, t must be very large, okay? It must be set very, very large. So usually if you set a large enough number of iterations, you are quite safe and you might be sure that it's not overfitting. An alternative is to use early stopping, exactly as we have seen with a neural network, which means we use a small validation set apart, where at each iteration we evaluate our ensemble, and as soon as we see that the performance of our ensemble on the validation set starts deteriorating, we can stop the algorithm. Okay, and this is it. Then the learning rate is also a delicate parameter. Boosting is also quite sensitive to the changes in learning rates. But the idea is that, similar to gradient descent, is that smaller learning rates are preferable because they will lead with more probability to good results, although they are usually slower. They reach, a good value is lower than larger learning rates. So always try to tune also this hyperparameter, also known as shrinkage. In AdaBoost, we have seen that the step size is automatically updated. The learning rate, a fixed learning rate, though, can be used to multiply the step size, the new step size at each iteration, although this is not necessary. And then you also have, exactly like in bagging, the hyperparameters specific of weak learners. And what is done usually is to use shallow trees. So a maximum depth between 1 and 8 should be fine. Some suggest that a default of 6 is a good choice. Someone else says 5. Someone else says 2 or 3, but the idea is always use shallow trees. You can also tune these hyperparameters if you want. Now here we see an example of how the number of iterations interact with the learning rate in boosting. We are in a classification case. Here we're observing how the accuracy changes in the train and test set as we increase the number of iterations and modify the learning rate. The tested learning rates are 0.001, 0.01, and 0.1. And what we can see is that the smallest of the learning rates, 0.001, the blue curve in the plot, is the one that takes the longest, to become effective, to kick in. So it takes more iteration to start improving the performance of our boosting algorithm. But once it does, after almost 50 iterations, it starts making the algorithm perform greatly. And we can see the training error and training accuracy and test accuracy increase together very quickly. And this learning rate soon becomes the one that leads to the highest test set accuracy, compared to the other two larger learning rates. And so if we were to use early stopping, for example, with this learning rate, probably early stopping will terminate the algorithm between 75 and 100 iterations in this case. Here we also see how the number of iterations interacts with the maximum depth of the tree, and I leave to you comments on this plot. Okay, now we are back to talk about ensembles in general. So we are also going to talk about bagging as well as boosting. And as you can imagine, while these methods that we have seen are very effective in improving the performance of our Bayes estimators, are not that great as far as interpretability is concerned. And this is because, as you can imagine, ensemble methods base their predictions on several, individual estimators rather than just one. So it's not easy to understand how to interpret these methods. However, if we use decision trees as Bayes learners, for example, and you remember how to calculate feature importance in decision trees, and if you don't, please go refer to that lecture to review how this is done. We can use, so what is done in practice is we consider the feature importances observed for each decision trees at each iteration, so at each bootstrap replication in bagging, at each tree of the forest in random forest, or at each iteration in boosting. We sum these feature importances across all the all the trees in the ensemble, and then we simply average it. Okay, so we divide it by the number of iterations, and these help us to obtain. So this is the way to obtain the final feature importance of the ensemble. And so, for example, if we obtain a plot like the one represented in section 4 of the notebook, we could say, for example, that in this hypothetical situation, we can say feature 5 contributes about 70.5% to determining the predictions of our target variable. Okay, and this is because all these importances are then normalized in such a way that they sum to 1, and so they can be interpreted as proportions. Okay, proportion of contributions of the feature to the predictions of our target, continuous target, or class in case of classification. And this is it. And of course, the same caveats we have seen in the case of decision trees are valid also for ensembles. For example, we don't know the direction of the relationship between the feature and the target. And also, we only explore, univariate relationships, and we don't know about possible interactions. Okay, then just another couple of remarks. So if you remember, I said before, we can see bagging as a parallel algorithm and boosting as a sequential one. And this fact can be used in bagging. Because since we are learning a lot of several independent Bayes learners for each bootstrap replication, then what we can do is we can simply parallelize the problem. And so if we are using a multi-core machine, we can learn each new tree in a core of my processor. However, in boosting, this is not possible because, of course, the results of an iteration depends on the result of the previous iterations. However, in boosting, because we are learning shallow trees, each iteration is going to be faster than bagging, where instead we have to learn, very deep trees, whose computations then becomes slower. We can also kind of bag boosting by using by at each iteration of boosting we can sample without replacement a subset of the units in the training set and use them to obtain an out-of-bag score. Although this might not be always ideal because then we will use less units for the training. And this is it. Then I left the link to the scikit-learn documentation if you want to learn more about ensembles. Now let's gonna check examples in Python. We are gonna see, for example, 2 regression examples with bagging and gradient boosting, and 2 classification examples with random forest and AdaBoost. For the classification examples, we're gonna use the half moons dataset already encountered with random forest earlier, and for the regression examples we're gonna use the Boston housing dataset, which you might already know by now. So bagging in Python can be run with 2 function, bagging regressor and bagging classifier, and it takes the following arguments: the base estimator, so the base learner that we want to use in bagging, the number of bootstrap replications, the maximum number of samples to resample at each iteration, the default value of 1, which I suggest you to leave, means just resamples as many observations, like a sample size equal to the number of to the sample size of my original dataset. And then finally we have the out-of-bag score, which is a boolean, and it's asking whether we want or not to that the algorithm returns the out-of-bag score that we have discussed previously. So let's go straight here. I'm using a linear regression model as base learner. It doesn't make too much sense in bagging because bagging needs high variance estimators, while linear models are usually very low variance estimators, unless we are in some specific case. But the reason why I did this is to show you that we can really use bagging with any base learner we want. Okay, so it's just an illustrative example. Okay, there's not a theoretical reason why I'm doing that. And so if we do this, we call the bagging regressor with base estimator a linear regression regressor. We ask for the out-of-bag scores. We use a number of estimators, a varying number of estimators actually, and I try every 50 number of bootstrap replications between 20 and 1000. Okay, so I basically am learning a number of bagging estimators that is larger than 1, where the number of bagged linear regression models is equal to 20, 70, 120, 170, and so on until 970 in this case. And then we can plot the results of number of bootstrap replications against out-of-bag score. And as we can see is that linear regression seems to slightly benefit from bagging as long as we don't use a too large number of bootstrap replications. But even even so, if you observe the scale of the out-of-base score, which I remind you by default, the score in a regression case is the R-square for scikit-learn. So the value of the R-square doesn't improve that much. You see, it's only 0.002 difference between the minimum and maximum value on the y-axis of the plot, which means probably didn't make much sense to use linear regression with bagging in this case for the reasons that I explained right now, just before. So the benefit of bagging is probably not significant with linear regression. Nevertheless, I think it was useful for you to see that we can actually use bagging also with models that are not just trees. So for example, I invite you to try to rerun this experiment with a very deep neural network, although this might take some time, or with k nearest neighbor with k equal to 1 and so on. So with these high variance models, in this case, I expect bagging to benefit. I expect these estimators to benefit from bagging. Okay, now next experiment is a random forest in classification case. A random forest in scikit-learn can be called with either random forest regressor or bagging classifier. The arguments are similar to the ones of bagging. We don't have the base estimator in this case because a random forest only uses decision trees as base learner. We can pick the criterion for the split. It can be the Gini or entropy in classification, or mean square error in regression. We can once again ask for the out-of-base score, and now we also have our M parameters. If you remember, is the number of features to sample when deciding to perform each split. Okay, we're gonna implement random forest on this half moon dataset, and what we do to call it is we call the function. We say we want 500 estimators. We use the Gini criterion for the split, and max features equal to in this case we're not giving a number, but we're giving the sqrt string, which means take the square root, okay, of the number of features, which is the default recommended in a classification case. And then we also ask for the out-of-base score. Now the results are the following. The out-of-base score is 90.9625. On the test set, the score, which is the accuracy in classification for scikit-learn by default, is 0.95. And the estimated decision boundary, we can plot it, results to be the following one. We can also ask for feature importance, and what random forest is telling us in this case is that feature 2, x2, contributes about 60% to the predictions of our class, while feature 1 about 40%. Okay? Now, let's switch to boosting. Gradient boosting also has two functions, gradient boosting regressor and gradient boosting classifiers for classification. We have the following arguments. So the base learners are always, the weak learners in this case, are always assumed to be trees. So the loss can be the least square loss, okay, or the deviance in classification, which is basically the entropy, the cross entropy that we have seen before. Then the learning rate for the of the ensemble, okay, the number of iterations of my ensemble, and then the criterion used to perform the split. And if you remember, we said the gradient boosting, the weak learners are always regressors. And so in this case, the default can be the mean square error for the split. And then we also have three specific hyperparameters. The max depth is usually the most important one. Okay, now we're gonna use the Boston, we are in a regression case, we're gonna use the Boston housing data again. We use 500 iterations of gradient boosting, we use the least square loss, a learning rate equal to 0.1, maximum depth equal to 1. So let's run the gradient boosting. We obtain a score on the test set equal to 0.86%, which I remind you once again is the R-square. So I invite you to try to interpret this number. Now we can call once again the feature importances according to gradient boosting. And what we can observe is that the most important feature for boosting are definitely RM, which is the number of rooms per household, per dwelling, and LSTAT, which contributes even 50% to the predictions of the target, which is the percentage of lower status in the population, okay, for that region of Boston. So let's try to plot these two features against the target and see if there seems to be some significant relationship. And indeed we see that the first feature, the most important one, LSTAT, seems to have some either piecewise linear relationship or linear with a curvature, and RM seems to have more or less linear one, not accounting for outliers. Okay, so boosting was able to retrieve, the relationship. We don't know the interaction of these features with other features, but we can see that these relationships were allegedly correctly picked by boosting. And now, last but not least, AdaBoost, which is a classifier. So we're gonna use it once again in our half moons data set. We call it by giving the base estimator, which is gonna be a decision tree in this case. We're gonna use a max depth of 1. We're gonna use run AdaBoost for 50 iteration with a learning rate of 1. So we can just use the the step sizes detected by AdaBoost without multiplying them by any other learning rate. And the results are telling us that the score on the test set is equal to 0.925, which is slightly lower than random forest. Of course, we can tune these hyperparameters to see if we can improve the performance. And the decision boundaries are the following one. We can see that with respect, compared to the one of random forest, they are much smoother because we are using base learners, weak learners as base learners, as base estimators. Feature importances are telling us something different here compared to random forest. Here they're telling us that 65% of the predictions, more or less, is determined by feature 1 and 35% by feature 2. Okay, for AdaBoost you can also implement AdaBoost in regression with AdaBoost regressor with scikit-learn, which has a similar functioning of the one seen for classification, but of course contextualized in a regression case. Now, last topic, I wanna quickly go through two other ensemble methods that we haven't seen yet. I'm just gonna list them and quickly describe them to you. Then if you wanna know more about them, you can just use the links I put in the notebook to read from the scikit-learn documentation how they work. So we have voting methods, which work in the following ways. What we are gonna do is we select a number of individual, estimators, can be regressors or classifiers, and they can be very different from each other. We can see, okay, let's use a SVM algorithm, let's use a KNN, let's use a neural network, let's use a linear regression, a logistic regression, and so on in a classification case. And let's perform predictions with all of these, okay, independently. And then what we do, we simply average, okay, the predictions of each estimator. And this is it. And this is how voting methods work. An alternative, we can also give a weighted average by giving a different weight to each of our estimators. So that we can say, for instance, give more weight to the prediction of logistic regression than to the one of KNN, for example. Now, stacking. Stacking works in two steps. Okay, in our first step, we have a functioning that's similar to voting. So we have several different base learners, can be KNN, SVM, and so forth and so on. But then what we do is we take the predictions of stacking, given by each of these base learners. You can see the representation here of stacking. We take this prediction of each of the base learners. These predictions become the new predictors, okay, the new features that we're gonna use for the prediction of the same target. These predictors are given as input of a new base learner called meta learner in this case. It can be also a logistic regression, a deep learning a neural network method, an SVM. The idea is we use these predictions as predictors to predict our target, and then the predictors provided by this meta learner are the predictions of stacking. The last ensemble method I want to talk about is actually a modification of gradient boosting called extreme gradient boosting, or XGBoost for short. And it is basically gradient boosting but optimized so that it's even faster than normal gradient boosting, and it also can provide more accurate results because it allows to better tweak, the complexity and to tweak the hyperparameters of our base weak learners. Okay, it allows for more for better regularization of the weak learners of the trees. So if you want to have a very powerful but also a very very fast ensemble prediction method, then XGBoost is the way to go. XGBoost is famous because it has led to winning several Kaggle competitions, so it has proven to be effective in several contexts. So this is an extremely useful tool if you are interested in prediction. It's not in scikit-learn. You cannot implement it from scikit-learn, but the authors of XGBoost wrote their own Python package. Actually, XGBoost is a library written under several programming languages, and Python is one of these. And you can find the notebook, also a link to the documentation page of XGBoost. Now, last but not least, I would like to show you an example of ensemble methods on the HERT dataset as usual. So we load the dataset as done so far. We're gonna compare random forest with AdaBoost, and we are gonna tune the number of iterations for both AdaBoost and random forest set between 50, 100, 500 and 1000. The learning rate for AdaBoost, since we're gonna use randomized search for the tuning, we're gonna give a reciprocal distribution to the learning rate, exactly as we have done with the learning rate of neural network. So try to check out the notebooks on neural networks in practice to see why we might want to use this distribution for the learning rate, although it's not necessary. You can use a uniform if you prefer, or any other distribution. Then the number of features, sorry, any other distribution that that's defined in the range of positive numbers, or in the that's in the domain of the positive real numbers. Now next, the number of features m to use to perform the splits in random forest, and we pick between 2, 3 and square root of p. Okay, after uploading, importing the data, we call the pipeline. We call the reciprocal distribution from SciPy, and we also call the randomized search CV function. We write our parameter grid. By now you should know, we should understand how to interpret this grid. So I'm not gonna go through it too much, also because I already presented the hyperparameters we're gonna tune. And then if we run tenfold cross-validation for 50 iterations, which is quite a low number, so if you want, try to increase this number at home by yourself to see what happens. We see that the best estimator is AdaBoost in this case, with a learning rate equal to 0.11 more or less, and run for 50 iterations. And this leads to cross-validation accuracy of about 84%, which is almost in line with what we have found with linear models, linear classifiers. If you compare it with logistic regression and linear SVM, you see we are pretty much in line. Those classifiers, the linear ones, are so far the best performing ones on this dataset. Here we also see the results for the 10 best classifiers, and here we also plot the results, okay, of random search, of randomized search. What we do here is we take the best classifier, so in this case AdaBoost, and we ask scikit-learn to report the feature importances, and we see the most important features for AdaBoost are chest pain asymptomatic and CA. So I leave to you how to interpret these results once again, and I also invite you to compare these feature importances with the feature importances or the regression coefficient of logistic regression, with the weights of linear SVM, and also with the results of decision trees. Okay, the feature importances of decision trees, try to check if they're similar, if they're different, and if so, what are the differences, and so on. Now, let's also assess the score on the test set. The accuracy on the test set is also about 84%, which is also almost in line with what we have observed with linear models. Okay, this is it for this lecture. It was quite a long lecture. I must admit I'm a bit tired. But I hope everything was clear to you, that you could learn ensembles. As an exercise, final exercise, I leave you like the chance to experiment a bit with ensembles on this hard dataset. So for example, you could try to implement bagging with some high variance estimator. You could try to also implement add gradient boosting to the list of classifier to search across. Gradient boosting can be with varying iterations, learning rate, maximum depth of the trees, and the same for AdaBoost. You can also try to tune the maximum depth of the trees. Try also, if you feel like, to implement stacking and voting classifiers if you want. Feel free to play around with it, and this also helps you to give a flavor on how to use ensembles in practice. I also invite you to try to increase the number of iterations of randomized search to search across a larger space. This was it. I repeat, I hope everything was clear to you. If not, you can write me emails or messages on Canvas. You can also try to contact us on Slack, okay? And so what is left now is a last lecture on, in which I try to describe you a bit how to perform an end-to-end project from scratch till the end in data mining. And this lecture is gonna be uploaded on Canvas on Tuesday. And then next Thursday, I think I'm gonna present the final assignment, or maybe I'm gonna do it earlier. No, I will think about it with Sibyl. And subsequently, on Thursday, I'm also thinking about having a big, final Q&A session, probably via Canvas. But I'm not sure about it yet. I'm gonna decide everything in the next days, and of course, check the announcements on Canvas to stay updated. Okay guys, so I wish you a good morning, afternoon, evening, depending on when you're watching this video, and yeah, stay safe and stay strong and stay healthy. Okay, bye guys.